Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into designing a ticket booking system, the kind of system that powers platforms like BookMyShow, Ticketmaster, and Eventbrite. We'll cover seat inventory, seat locking, flash sale concurrency, idempotent payments, waitlists, and the full low-level design. Whether you're preparing for a senior engineering interview or building a real-world ticketing platform, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into designing a ticket booking system, the kind of system that powers platforms like BookMyShow, Ticketmaster, and Eventbrite. We will cover functional requirements, non-functional requirements, system architecture, end-to-end user journey, core models, low-level design, and the trade-offs that come up in a senior system design interview. If you are preparing for a FANG interview or building a real-world ticketing platform, this one is for you. Let's get into it. Here is the core problem. A popular concert or a new movie goes live and hundreds of thousands of users hit the app at the same time to grab the best seats. Seat inventory is limited, users abandon carts, payments fail, and duplicate requests can accidentally reserve the same seat twice. If the system does not handle seat locking, inventory consistency, and concurrent access correctly, it will oversell tickets, leave customers angry, and create a massive operational mess. The challenge is to let users browse, select, hold, and pay for seats while keeping the inventory accurate, the response fast, and the experience fair under extreme concurrency. Let's walk through the functional requirements. First, the system must let users search events, venues, showtimes, and seat categories with filters like location, language, and price range. Second, it must render an accurate seat map that shows real-time availability, block seats, and pricing tiers. Third, it must let users temporarily lock selected seats while they complete payment, so no one else can grab them during the hold window. Fourth, it must process payments securely, handle failures and retries, and confirm bookings with tickets and QR codes. Fifth, it must support order management, cancellations, refunds, waitlists, and notifications via email, SMS, and push. These capabilities make the platform usable, reliable, and fair. Now the non-functional requirements. The system must be highly available, because ticket sales open at a fixed time and traffic spikes instantly. It must be strongly consistent for seat inventory to prevent overselling, while still remaining eventually consistent for analytics and search. The booking flow must be low latency, especially the seat selection and lock steps, because users will refresh aggressively if anything feels slow. The system must scale horizontally for flash traffic and handle millions of concurrent users. It must be secure around payment, fraud, and account takeover. It also needs idempotency so that duplicate clicks or retries do not create double bookings. And finally, it must be observable, because a ticket drop is a high-stakes event where every second matters. Here is the high-level system architecture. Users come in through a CDN and a mobile or web application. The API gateway routes read traffic to a search and catalog service backed by caches and Elasticsearch, and write traffic to the booking service. When a user selects seats, the booking service talks to a seat lock service, which uses a low-latency cache like Redis with TTL-based locks to hold the seats for a few minutes. The inventory service tracks the authoritative seat state in a relational database. On successful payment, the payment service publishes an event, the booking service commits the seats, generates tickets and QR codes, and the notification service sends confirmation. Analytics and fraud services consume events asynchronously. This split between read-heavy catalog traffic and write-heavy booking traffic is the key scaling decision. The key metrics to memorize cold. Seat occupancy rate, the percentage of total seats that are eventually sold versus left unsold. Inventory consistency, the number of seats that are double-booked or oversold in a given window. Booking throughput, the number of successful bookings per second during a flash sale. Average seat lock time, how long users hold seats before confirming or abandoning. Payment success rate, the fraction of initiated payments that complete. P99 latency for seat selection, lock, and payment initiation. Waitlist conversion rate, the percentage of waitlisted users who get a seat when one becomes available, and system availability during a ticket drop, measured in nines. These are the numbers that business and engineering care about most. Let's trace the end-to-end user journey. A user opens the app, sees the upcoming concert, and filters by city and date. The seat map shows available, blocked, and already sold seats in real time. She picks 2 adjacent seats, which the system holds for 5 minutes with a countdown timer. The price, fees, and cancellation policy are shown clearly. She enters payment details and completes the transaction. Within seconds, the booking is confirmed, the seats are marked sold, and the tickets land in her email and app with QR codes. If she abandons the cart, the lock expires and the seats return to the pool for others. If seats are sold out, she can join a waitlist and be notified if a seat opens up. The core models and algorithms. The seat map model represents the venue layout, sections, rows, and individual seats with attributes like price, accessibility, and status. The inventory model tracks available, locked, sold, and reserved states per seat. The seat lock manager uses a TTL-based lock or a relational pessimistic lock to prevent double selection, while keeping the hold time short. The booking service orchestrates the flow. Validate seats, lock, process payment, commit or rollback, and release lock if payment fails. The payment service must be idempotent, meaning a retried payment with the same idempotency key always returns the same outcome. The waitlist model uses a queue to notify users when a seat becomes available, typically in FIFO order. The key trade-off is between lock granularity and concurrency. Per-seat locks give better fairness but more coordination overhead, while section-level locks are simpler but can reduce throughput. Now the low-level design deep dive. The bookings database has tables for events, shows, seat inventory, seat locks, bookings, payments, and waitlists. Critical inventory queries use optimistic or pessimistic locking at the database level, or an atomic decrement in Redis, to guarantee consistency. The booking flow is modeled as a state machine. Seats selected, locked, payment pending, payment confirmed, tickets issued, or payment failed and seats released. The lock service uses a Redis key with a TTL, maybe backed by a red lock or a database record for correctness. Idempotency is enforced at every retriable step. The user request has an idempotency key, the payment gateway has a unique transaction reference, and the booking confirmation is checked before duplicate inserts. For read-heavy seat maps, caches are used with short TTL and invalidation on state change. For scale, the inventory can be partitioned by event or venue, and the booking flow is isolated from search and analytics traffic. Key takeaways for your interview. First, a ticket booking system is a concurrency and consistency problem above all else, so start with inventory, seat locks, and idempotency. Second, distinguish between fast reads like search and seat maps and the slower, strongly consistent writes like locking and payment. Third, explain how you prevent overselling using atomic inventory updates, short TTL locks, and payment confirmation before final commit. Fourth, cover idempotency and retries for payments and booking creation, because duplicates are a common failure mode. Fifth, mention the waitlist, cancellation, refund, and notification flows to show you have thought about the full user experience. If you can walk through this system with these 5 points, you will signal strong senior-level design thinking. That's it for designing a ticket booking system. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on designing a ticket booking system. We covered the full picture, from seat maps and inventory locks, through payment idempotency, waitlists, and the low-level design of the booking flow. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.